Hey there, welcome to a video discussing section 1.7 part 2, composition of functions. So on Wednesday, March 15th, during our Zoom class, which we had because there's no power to the Sacred Heart campus, we covered 1.7 part 1, but now I'm doing 1.7 part 2. So this will be a homework, part of homework due Friday, because I don't want to spend too much time talking about this on Friday, and hopefully we are in person on Friday, because we do need to finish chapter 1 by doing 1.8 on Friday, and then review for our test next Tuesday, and then have our test on Thursday next week. So anyway, definition of composition of functions. So a composition of functions is when you plug one function into another function. So usually it'll look like this, where g of x being plugged into f of x. So that's the definition of composition function when you plug one function into another function. Now, domain, you're going to have to consider domain of the inside function. In this case, inside function would be g of x. Also, consider the final expression that you get when you work things out. And any of the intermediary steps. So any steps along the way where there could be a restriction, you're going to have to consider that. So that's what's going on there. So now let's actually put this in practice. So first off, we're just going to focus on composition, then we'll do domain afterwards. So here we're plugging a function into a function. So when you see this here, where it looks like an open circle, it actually means f of g of x. Just a shorthand notation, I suppose. So you're going to replace x here, x in the f of x equation, with x squared minus 2x. So instead of 3x, you're going to be plugging in x squared minus 2x plus 6. Then when you distribute, you should get 3x squared minus 6x plus 18 minus 4. So the composition would be 3x squared minus 6x plus 14. Should be pretty easy, right? Now the other way around, g of f of x, so you're plugging f into g now. F goes into the g function. So you're going to have something squared minus 2 times something plus 6. So in this case, it's going to be 3x minus 4 and 3x minus 4. So that's what you plug in. So when we work that out, you should get 9x squared minus 24x plus 16 negative 6x plus 8 plus 6. And we'll just simplify it. You should get 9x squared negative 30x plus 30, I think. Yeah, plus 30. Easy peasy, right? There you go. And then last, g of f of 1, you're plugging 1 into the f function, and then whatever that output is, you plug into the g function. So f of 1, that's easy. That's 3 minus 4, which of course is negative 1. Then that goes into the g function. That would be negative 1 squared minus 2 times negative 1 plus 6. That's 1 plus 2 plus 6, which should be 9, I think. Or you could plug into this one right here. Since we worked it out, if you plug a 1, you get 9 minus 30 plus 30, which is still 9. So that's all. Sat C. Okay, let's do this again. F of g of x. Now, in this case, we got two fractions here, or two rational expressions. So doing f of g of x. So you have 2 and then blank minus 1. So you're replacing x here with all this. So you put 3 over x. So that is our expression. You could clean it up if you want to, but I think it's fine if you leave it like that. But the domain's a little tricky though. So what you'll have to do is you do have to consider g of x, because that's the first thing x sees is a g of x function. So we know x can't be 0. That's for sure. Because that'd be a problem. If you plug in 0 into g, if you do f of g of 0, you're gonna have a problem because you're gonna have something that's undefined right from the start. So that's not okay. Also, we have to guarantee that this whole denominator does not equal 0. So that would be a problem as well. So 3 over x equals 1, cross multiply x equals 3. So also x cannot equal 3. That would also be a problem, because then they would make this 0, and that would be bad. If you were to simplify this fraction, if you were to go a little further with combining things, I guess I have 3 over x minus x over x, or 2 over 3 minus x over x. So you get 2x over 3 minus x. So yeah, that kind of confirms that, yeah, 0 would have been bad right from the beginning, and 3 is also bad as well. So your domain is going to be then from negative infinity to 0, from 0 to 3, and from 3 to infinity. That'd be the so you really have to consider not just the beginning, but also what happens at the end. And also, you just never want denominators to be 0. That's just always bad. So it's not quite a hard and fast rule of like, okay, well, here's what you have to do. It's not procedure. You really have to kind of take a step back and say, okay, well, here's my function. Here are restrictions that could happen. Like, have x in the bottom of the fraction. Those, whatever fraction I have, can't have 0 in the bottom. We have 3 over x as a fraction. Of course, you can't have 0 in the bottom. And then overall, you have a big fraction, 2 over 3 over x minus 1. So the new denominator, 3 over x minus 1, that also can't be 0. So we got to work that out as well. Let's do g of fx. So remember, g of x was 3 over x. So you have 3 over all this junk. And instead of x, you're going to put 2 over x minus 1. So remember, g of x was this, and f of x was that. So this whole thing replaces the x in the 3 over x expression. So right from the beginning, I know x can't be 1. But let me work it out to see what we get in the final answer. 3 over 1. Got to flip it over. So you just get 3x minus 3 over 2. Well, I mean, 2's in the bottom, so who cares? That's totally fine. So really just x can't be 1. That's the only restriction we got. Again, I don't have radicals, like even rooting. And 2 over x minus 1 itself, I mean, you can say that equals 0, but again, we know that when you solve that, oh, sorry, that was dumb. You multiply x minus 1 by 0. I was multiplied by 1. Oops. Yeah, 2 obviously doesn't equal 0. Yeah, you can never make 2 over x minus 1 0 because the top is 2. So that's your domain for that one. Okay, we've got one more page and then we're done with this notes. So here you're asked to decompose. So you're asked to express h as a composite of two functions. So really what you want to do is to decompose. Now, if you want to be a real smart ass about it, you could say this. So basically h of x is going to equal f of g of x, and you're trying to find what f of x and g of x are. So again, if you really want to be a smartass about it, you can say g of x equals x, and f of x equals whatever h of x was and call it a day. You could do that, but I will put a condition that you can't do that. So you got to be a little more creative than that. What I would do is let g of x equal the inside the radical, which is x squared plus 1. Let f of x be the cube root of x. Therefore, f of g of x is going to be the cube root of x squared plus 1. So it gets you back to that. Or here, you can let f of x will be outside, g of x will be the inside. You can let g of x be x minus 2, and f of x be 1 over x. That could work. Because when you do f of g of x, you get 1 over x minus 2. So there's not really just one way to do it. You could have been even more creative. You could have said, like for example, for b, you could have said f of x is 1 over x plus 1. And you could say g of x is x minus 3. So you replace x minus 3, you do get 1 over x minus 2. You could have done that if you wanted to. So there are infinite possibilities. But that's how you would decompose. Just kind of good to get, to know how to decompose, so that way you get a deeper understanding of composition of functions. Okay, that concludes the video.